again. So lab 3 was doing what? Somebody tell me. Lab 3 was doing what? You already have 16 LED, and then you are just like swapping the time with it, right? So
Hmm.
this amount of time this LED will be on. Then this amount of time this LED will be on. This amount of time the LED will be on, right? If you go and you remove this LED and you connect it to the AN of the digits, how many digits of this you have? So instead of 16, just have 8, right?
Yeah.
Then in the document say that you have to run in the something kilohertz, right? If you flip to time, you will figure out every single digit you have to be on for this amount of time. Then you flip to the other one. So what you are doing, and basically you're doing something called time muxing, which is the
Hmm.
same thing as lab 3.
So as long as we show that we have control over the LEDs on what number they are when, it should be fine. Because I ended up designing like this whole overflow
No,
BCD
no, no,
counter.
no, that's cool.
Yeah.
Actually, that can be, that would be possible things. But of course, that's really good.
It,
That was one of my labs like a couple of years ago.
so if I present you that, that should be okay, or should it just?
I'm fine with that. I'm fine
Oh,
with it.
okay.
But at least tell me. Do you remember what I said in the record? Right? I said, I want you to fix a problem I made, and
Yes, I did find that problem.
perfect. And then you will spell it out. Say that here was your problem, and here how I fix it. Then you're
Hmm.
gonna make a test benches, right?
Hmm.
And also you will deploy the counter on the board with with that digit that will show me 0 to 9,
Oh, okay.
right?
Sounds good.
Did I say speed, right? I said also speed.
Oh yeah, the switches control the speed at which the counter goes.
Yeah, so
Correct.
the counter,
Yeah.
0 to 9 will be really fast, and you already learned the trick of the speed, right?
Yeah.
From the lab 3. So,
Hmm.
have you noticed now I'm trying to accumulating labs to build something bigger?
Definitely, I see it.
Yeah. Any other questions, guy, regarding the lab?
Are there restrictions for the lookup tables and flip-flops for the entire design? Because I don't think you mentioned.
Uh, we are in week what? We are in week
7.
7, right? So, uh, do your best. Just try to get closer.
Okay.
But because in a certain time, I will come and say you have to get these numbers.
All right.
So I'm just trying to how to say, to make you get used to it, basically. And once you will get used to it, then it will be easy for you to fulfill the requirement. That makes sense.
Yeah.
Okay. Any other questions? One of the things I want you to learn, every time you write a piece of hardware, a piece of Verilog targeting hardware, you have to write a test bench to test this before you will go to the hardware. That makes sense? Because if you notice, the Vivado, it takes a lot of time until it will synthesize something, right? And imagine that you made some mistake and you're synthesizing it. Then you will go into the board. It will not work. End of the day, what you're gonna do, basically, you are wasting time. But if you cut all of the errors before you will go for the final synthesis, then you will just do it one or twice maximum, and then the target will be. I mean, you finish the whole entire mission, right? That makes sense. Anyway, now we need to talk about the rest of the timing, and after we finish the rest of the timing, we will talk about how can we build a memory using Verilog. So here we're gonna have a series of memories. So basically we're gonna learn something that's called a memory as a memory, and then we're gonna learn out of this memory how can we build something that's called FIFO, which stands for FIFO, first in, first out buffer. Then if we have some more time, we can talk about the beginning of the finite state machine. In a certain time when I will teach you finite state machine, I will teach you also how to build a driver for the UART. So you can send from the C code in the computer some data through the UART cable, and maybe we can push it into the VGA, the screen, or we can push it into the digits, so you can see number coming out of the program coming from the computer, stuff like that. You know what I mean? That's one of the serial communication protocols we're gonna learn in this course. Sounds good?
Professor,
Yes, sir.
does the UART have to come through the UART cable port, or can it be through one of the PMODs on the?
I will show you this. This is an extension from PMOD. It's called PMOD UART. Can you see it?
Oh.
So this
Yeah.
one, this one, it has the chip, because the UART is tied by something it's called FT, which is a microcontroller. Look at this little itty chip on it. The black part on it, right? Can you see it? So that one is actually the chip for the FTC, for the UART. So you can mimic the UART, just having a wiring from the PMOD here to PMOD there, but it will not be efficient as if you have a boost signals processing inside this. So one of the possible projects you can ever see, in which never actually been seen, you can put multiple PMOD like this here, like 1, 2, 3, 4, 5. You can put 5 of those, and those 5 will be going into another board. And the other board will go to another board, another board will go another board, and you're gonna make a topology of the multi-nodes. Then the last one will be connected to the computer, and it will send data to them. So you can build like a cluster.
So that those UART chips are wireless, or no, they're wired, right?
Still, you're gonna connect your wire, right? It's
Yeah.
wire to
Mhm.
wire. There is
Yeah.
another, there is another one. It's called Bluetooth PMOD, or wireless PMOD. There is GPS PMOD. So I can put the GPS PMOD here, and then satellite will be communicating with the board.
So with that chip, you don't have to program the UART.
No. You have to do something else. It's another protocol, SPI. So actually, there is a couple of protocols. There is SPI, there is I2C, there is UART, there is PCI, there is PCIe. Maybe I can open my tablet and start writing so you guys can remember these expressions. One second. Excuse me. Everybody can see my screen, right?
Yeah.
Okay, so we have a serial communication protocol. It's called serial communication. Those are one UART. Okay, the second one, it's called SPI. Third one is called I2C. Fourth one is called PCI, and this is retired. You can find in a really old generation board like Vertex 2, Vertex 2 Pro, and stuff like that. Then 5, you can find the PCIe, and those of generation like Gen 1, Gen 2, Gen 3, Gen 4, Gen 5. Okay, and then whatever you can build like this 7-segment display, Ethernet also. You have Ethernet. You have VGA. you have USB, you have HDMI, you have DVI, stuff like that. Okay, look. So UART, all of them are actually all of them are working using the philosophy of the finite state machine. All of them using FSM. That's why I'm trying. I'm very slow with you just so you can digest the idea. But after that, I will speed up a little bit. So you're gonna take a finite state machine, okay? And then you're gonna learn about UART. You're gonna learn about SPI. SPI is networking of device talking to each other, okay? Is used more into those two guys are used more into robotics. I2C, because the speed of sensors, like, you have a little bit of sensors checking the temperature, then, I2C will be used. You have, for instance, pressure sensors, I2C. You have, for instance, radiation sensor, I2C, stuff like that. Because you know what, the physical phenomena this sensor is tracking or observing is really quite slow. So at the end of the day, you have to run in a really low frequency. Okay, then you need to learn how to buffer data, to save data. That's why we're going to learn something that's called Fifo. So Fifo is not just one thing. Fifo is a multiple things. So, normally we learn here buffer. And the buffer, we have Fifo, we have LIFO, and we have Philo. And of course, you have LILO, stuff like that. You know what I mean? That makes sense? Okay, look. So
Yeah.
FIFO, it means first in, first out. Like you already have a buffer like this. Whatever you keep pushing, it will get out here. That's called FIFO. LIFO, that means, you keep pushing, but then the last one will get out. This one, it has an example in software. Somebody can, if you are really good on software, tell me what is the LIFO is as a software example.
A stack?
A stack. Yes. This guy is tricky. A stack. A stack pointer work as a, LIFO track. Philo, first in, last out. And then, last in, last out, which basically, you flip it up. Okay. So to learn buffer, you have to learn memory. Right? To learn memory, you have to be very good in what? Verilog. Then, I can teach you how can you build the memory. That's why I'm very slow in this part. Then once you build buffer, you can use the buffer for storing data in UART. You can store data coming from SPI. You can store data coming from I2C because the speed rate. I will give you an example. Imagine that, this device is running in a speed 1, and this device is running in a speed 2, right? And I want these two guys to talk to each other. What will be the optimum communication device we will add here? Somebody can imagine what it will be. A buffer. So you can have a buffer like this, which is FIFO. And it will actually dump the data here. But then, it will write inside the FIFO with the S1 rate, but it will pull data out of the FIFO using what? The S2 rate. So now you understood why buffer is very important. That makes sense? Everybody align with me? Okay.
So they don't need the same baud rate if you have a buffer. It'll just fix it for you?
I mean, the buffer, I will tell you, there's a trick in the buffer. The buffer, it has to have something called flags. So the flag is like, there is a flag when this FIFO is empty, it say empty. There is another flag when this FIFO is full, it will be full. So you will not push more data, right? So that means, you can make this one idle until, the full status will go down. Then, there is a new place that can be holding data and so on. So it's a more logical thinking of how can you build a controller, which is a part of using FSM, finite state machine. Okay, look. Then PCI, it's a very old version of the PCIe. How many of you heard about PCIe? You know what's PCIe, right? Have you ever seen PCIe? How many of you seen PCIe? It is in my desktop. He's right. You know, I can show you PCIe. Here is PCIe. Excuse me. That's PCIe. This is part. This part. PCIe. It's stands for the PCI, but it's serial PCI, and it's running really fast and already high frequency, and it uses something called Handshake Design. How many of you heard about Handshake Design? I can tell you what is Handshake. So Handshake is the following, right? Here is the device 1, and here is the device 2, right? Those the two devices would like to use Handshake. So then, you know, we're gonna do something weird. You know what? We're gonna send the request. So S1 will send request to who? S2, saying that, you know, can I send you a data? Then, you know, S2 will send acknowledgement, ACK, say that, you know, yes or no. Okay, so let's say that, you know, the ACK said 1, that means yes. Then what? S2 will send the data. Then, you know, S1 will send the data. Then S2 will send ACK, say that, you know, no more. Right? Then, you know, once the ACK will be cleared up, then, you know, the S1 will send another request. Whatever I stored here and I mentioned to you is called Handshake. Like when, nice to meet you, my name is Muhammad, you know, you reply back and say, nice to meet you back, you know, I'm Christian, or I'm Lewis, or I'm Kingson, or Mario, Eduardo, and so on. That's called Handshake Design. Okay, look, I don't think we have time for going into the PCIe, but if you guys like me to do the PCIe and the extra thing, I can do it. That's fine. Okay, Ethernet. How many of you heard about Ethernet?
I think just about everybody has.
Did you see it? This guy. Network connection, exactly. And there are two different types of protocols for it. One is called UDP, one is called TCP/IP. That's something we can learn. Then, you know, there is VGA. You know, you checked your monitor, right? In the monitor, you have multiple things, right? You have VGA, you have HDMI, you have DVI, you have micro HDMI, you have all of those guys, right? Those are protocols for what? 2 dimensions or beyond 2 dimensions data representation. Because, you know, screen is what? Bunch of pixels going back and forth in a horizontal and vertical movements. So that's the VGA. It's one of them, which is initiated and started by IBM. Then, you know, they start the other companies and other, you know, standardization or authorities for getting the upgraded version. VGA is more analog. HDMI and DVI more digital control. Then the USB, right? Here is USB. That's also using the handshake approach. Okay.
Can USB be any form of serial communication, or is it just that handshake?
I would recommend handshake.
Oh, but it is able to go between.
I mean, you can do any formation you want, but, you know, because the USB has a problem. You know what is the problem with USB? It's a multi-layer. There is a formatting layer and there is a hardware layer. Like, for instance, you know, you have a SD card, and this SD card connected to USB stick, right? Then how can you communicate with it? You know, there is 2 parts of it. There is data format, like a soft part, you know, you're gonna store data, and hard part, which is basically ACK and request. So part of it is handshake.
Oh, part of it's always handshake.
Yes, it has to be. Otherwise, you know, you will cause something called hazards. Because, you know, you might dump data in a wrong place and you will start looking for it and you will never find, right?
I see. So beyond the handshake part, if it was given like UART or something,
Yeah, I
it
mean,
would hand off you.
yeah, UART is one of the handshake.
Oh, okay, okay.
Also, we have SD card. Have you guys seen this SD card here? There is also a way of programming this FPGA board using SD card. So we write here SD card. I'm gonna show it to you if we have time today. I mean, we have until 2:15, right? So I can show you a lot of stuff today. Okay, anyway. So is it clear to everybody so far, you know, how it is important to fully understand what is Verilog means, and how can you feel Vivado, and how can you program? Your strong knowledge in digital logic design will help you, and it will make it very easy for you. And of course, the software perspective, like, you know, when, you know, Kingston replied and said stack, that's something appreciated, because if you understand stack, then, you know, building it is not really hard, right? Okay, anyway, let's go back into the slides and see where did we start. We finished this part last time, right? So what I'm gonna do, I'm gonna give you another patch of slides, and I will continue on it, and then, you know, we'll return it back to this up-down counters things. So we are 3300, right? Excuse me. Courses. Second. I'll give you this already. Okay, so I'm gonna now share with you. You guys, all of you can open the Blackboard now, and you will find a folder there. Blackboard. So if you like to write any notes on the slides, that would be good. Okay. We are week 7, right? Week 7. There we go, and sign. And then we'll say supporting material. This lecture 8. Okay, you guys can now open and you'll find it. Okay, I already loaded there. Now I just will take a copy for myself. Right? Okay, it's already there. So let me get it for you. Screen is stopped, right? So. Everybody can see the screen now? Hello?
Yeah.
Okay, and you already have also a copy. Did you find it? Can you check the blackboard, everybody?
Yeah, we got it.
Super. So, at least you can align while I'm doing this. So here's the thing. So now we need to talk about what other perspective. In the timing, we talked about what? We talked about setup time, we talked about hold times, and we talked about STA, and we talked about violation. Let's remember what those guys are. Here is my clock, right? And the clock is what? Repeating itself. Then if I color it up like this is the positive edge, this is the negative edge. This is the positive edge, this is the negative edge. That makes sense? So here, positive edge, negative edge, positive edge, negative edge. Right? Setup time, the amount of time before the tick will happen, that means the positive edge will happen, that the input, it has to be what's stable. If it's 1, stay 1. If it's 0, stay 0. Okay? While the hold time is the amount after the tick. The input still also has to be stable, 1 or 0. Otherwise, you're gonna go in what? If you don't satisfy this, or you don't satisfy this one, we will go where? In something called metastability. That means the output will be crazy. Might see the 1 as an output, sometimes you see it as a 0, sometimes as an X. Why? Because any wire can hold X or 0 or 1 or even Z. Right? Z, high impedance. That means this wire is floating like this, flying in the air. Nothing's connected. X, that means I have no idea. I don't care what is going on inside this wire. 0, that means it's connected to the ground. 1, it means it's connected to the source. Do you guys agree? Then we calculated something that's called STA, which is the static timing analysis. We came into the static timing analysis, said that if I don't satisfy the timing, then I will have something that's called violation. Then, we stopped playing with the passes, and, we came into the, how can you define passes? What is the critical path? How can you calculate the maximum frequency? And we stopped in there, right? Now we need to talk about some aspects of having multiple clock domain. What does it mean? Now, there is 2 different approach of building a logic circuit. One is called synchronized, and one is called asynchronized. So we have synchronized and we have asynchronized. What does synchronized mean? Synchronized mean every single sequential part or circuit or module in the whole entire system is using and demanding and driven by the same clock. Example, if I have here a flip-flop, and I have here another flip-flop, and I have here another flip-flop. Inputs going like this, input like this, maybe the input going like that, I'm sorry. And then like this, and here's another clock. When I said this circuit is synchronized, so that means I have to be sure that this clock and this clock and this clock and this clock are just connected to one source of the clock. Then those 3 flip-flops are in a synchronization model or in a synchronization condition or case. That makes sense to everybody?
Yes.
Okay. But if any of them or all of them are running in a different clock system, that's called what? Multi-clock domains. Again, if I have here this flip-flop and this flip-flop and then another flip-flop and then here another flip-flop, and this connected to clock 1, this is clock 2, and this is clock 3, and this is clock 4, then I built up something is called what? Clock domain. Multi-clock domain. Again, what's called multi-clock domain. And this is one of the most difficult assignment you can get ever while you are designing a circuit. Guess who can help us to actually make it easy? Somebody tell me an idea. If you are, let's make it easy. If I have here two flip-flops, one is running in the clock 1 and one is running in clock 2. What is this? Right, one is clock 1, one is clock 2. What is the best way for moving data from this one to that one? You need something in the middle.
A multiplexer or a combinational circuit.
Buffer.
Maybe.
Right? Because this is running in a speed and this is running in a different speed. How are you gonna deal that, you know, this one will not spill data out? So basically you have circuits here and you have circuit there, and then you will build here a buffer. This one will be with this clock and this one will be with that clock. By this way, you will be able to move the data from this one to that one without any problem. That's why when I started my discussion today, I started out telling you about this buffer things. That makes sense? Then there is another form of the multi-clock domain. It's called asynchronization or asynchronized circuit. Again, there is another form. It's a slight form coming out of the multi-clock domain. It's called what? Asynchronized. Asynchronous. What does it mean? It means the following. It means that, you know, if I have here a flip-flop, the clock out of the flip-flop number 1 going to flip-flop number 2, it will be actually the output of the flip-flop number 1. So this is an output of this flip-flop, and this is flip-flop number 2, and this one. Since I took this one as an output, but then, you know, I use it also as a clock for the second one, what I'm doing, I'm actually trying to what? Control one by speed of the other one. What does it mean? It means the following. It means that this guy have a clock which is called clock. But then, you know, this gentleman, his clock now is what? Clock divided by 2. Then if I have a third stage, the output here will be here, and then, you know, I connect it also as a clock. Then it's gonna be clock divided by 4. This one remind you by what? The clock divider I taught you from the counter. Right? Because if you remember, you have here n bit. Here is 2 power 1, 2 power 2, 2 power 3, 2 power n. So that means, you know, the first wire, that means is dividing by 2. The second will be divided by 4. The third will be dividing by 8, 16, 32, up to whatever. That makes sense? So now we learn. We have in the approaches, if we are talking about sequential circuit, we have 2 things. We have synchronized, we have asynchronized. Asynchronized is a kind of what? Part of bigger system is called a multi-clock domain. Okay, look. So definitions, you know, something you can use for exams or, you know, internships, interview, or like final interview if you are going to work for a company or whatever you would like to do. So clock is used to synchronize the operation of all flip-flops, registers, and counters in the system. Pretty much is controlling every single sequential part of the circuit. That makes sense? Synchronized circuits are more reliable than asynchronized circuit. But is this a statement will give me a conclusion that avoid asynchronized circuits? Of course not. Let me tell you a story. Every single approach, it has its own pros and cons. Okay? The pros of the asynchronization is actually very small in number of resources. It's very small and tiny of number of resources. So pretty much you can come and assume, and you write here a conclusion, say that, you know, async, very good for the low power activities. And this is basically what you guys are doing, lab 1, lab 2, lab 3. You're trying to hit low power. That makes sense? Somebody will come and say, hey, professor, but you know, how is those labs are asynchronized even we put clock so it's synchronized? No, it's not. It's not actually completely synchronized because there is combination circuit in the middle. So number of resources are used for the asynchronization is completely less than the number of resources used for the synchronized. Then application-wise, you will find that asynchronization circuit or asynchronized approach are used heavily for something is called IoT. How many of you heard about this? IoT. It stands for Internet of Things. So there is actually Internet of IoT, IORT, IOTT, like this. Here, Internet of Things, Internet of Robotic Things, Internet of Tiny Things, Internet of Industry Things. And there is another one, it's called IOMT, which is Internet of Military Things. It's a very big, it's huge. It's like, you know, many applications you can think about. Pretty much it's like if you build a controller for sensors. Like imagine that, you know, you are deploying a bunch of sensors behind enemy lines, you know, and you're trying to, for instance, track their trains before you will send the bomber to destroy something, you know. Then, of course, you need to throw little itty-bitty tiny sensors, very cheap in power. So, you know, they're going to stuck there for like a couple of days or a couple of years. I don't know. It depends on how long you would like actually to track them, right? Anyway, so in synchronized circuit, events are expected to occur immediately following the active edge of the clock or the negative edge of the clock here, or negative. Not that many people use the negative edge of the clock. Majority of designers, they are using the positive edge of the clock. It's something, you know, people got used to it pretty much. Okay, but you still, you know, you can actually turn off all of the positive edge and you work with the negative edge. There is no problem with that. Also, output from one part have a full clock cycle to propagate to the next circuit, which makes sense, right? Because, you know, you are waiting for the next positive edge. That means you are waiting for whole entire cycle, then, you know, another whole entire cycle, because you start from the positive edge. Make sense? Synchronized design make design and debugging easier. It's easy for you to debug. Do you agree? Because at the end of the day, what you're gonna do in the waveform, you will look to the clock, the clock generation, and you will start looking to every single positive edge of the clock, and you will see what other signals happening while the positive edge is happening. So you have a guidance, you have a marker. You know, you will look into the positive edge every time. Asynchronized design, it should be closed here. Asynchronized design, although it can reduce power consumption, as I mentioned before, it is very difficult to get timing issues under control. So that means the percentage of getting violations based on the STA we learned from the first lecture will be higher. That makes sense? Hence, despite their high power consumption, designers favor synchronized design. So look, so the synchronized design has what? High powered consumption, but people like the easy missions, right? You know, if somebody offer you to work in 2 different projects, one of them is completely miserable, hard, difficult, while the other one is a straightforward thing. Which one are you gonna pick? You're gonna pick the most easy one, right? Unless there is some, you know, reward system, like, you know, I'm gonna give you $1 million if you finish this project. Of course, you're gonna work on the difficult one. So till now, you guys fully understand me, because, you know, now we're gonna go into equation and heavy stuff. So far it's clear?
Yes.
Okay, continuation here. Now I want you to have to imagine what's happening, okay, before we read this together. In the historical part of this of VLSI, how many of you heard about this term, VLSI? So in the history of the VLSI, what does it mean, VLSI? It's a very large scale integration systems. What does it mean? There is a semiconductor here, like a piece of semiconductor. What is the piece of semiconductor you have on your board? Somebody tell me. Where is the piece of semiconductor I have here? It's a chip. Any chip I have is a piece of semiconductor. That makes sense? We are using semiconductors. We are in the era of the semiconductor. What does it mean, semiconductors? You know semiconductors, right? It's something is not conducting 100%, it's not isolating 100%. Something in the middle. Okay. So every time we are trying as a chip makers and industry to have more transistor fitting in a small chip, everybody agree? Then you will be able to build more processors, you build more computation, you put more memories, you can put whatever you would like to put inside that chip. But then there is no lunch for free. What does it mean? When you are getting everything smaller, so that means here is a transistor getting smaller and smaller, and you are densing it. So what will happen? You are getting closer to each other here. Then you will cause to have something is called parasitic capacitance and parasitic resistance. It's more heat, yes, but those are different. Parasitic capacitance and parasitic resistance. Think about it. Now I have this little itty bitty transistor like this, right? And I'm doing routing. What does routing mean? Routing simply that means I'm connecting between points, right? Like in 2300 lab, what you guys are doing. Basically, we're bringing the breadboard, right? And you have a bunch of wire. Put the wire here, put the wire there. Put the wire here, put the wire there. In a certain moment, you will have a jungle of wires. That makes sense? And if you have a jungle of wires, what will happen? If any mistake happened, you have to pull out everything and start from scratch. Do you agree? Here is different because everything is automated. So you're going to be close to each other like this. So you already have here wire, and those points are connected to each other. Can somebody tell me, this one, it looks like what? It does look like what? A capacitor. So it will build kind of a capacitor, but it's not exist. That's why they call it parasitic capacitor. It's not exist. It's like a stray, something virtual. And that will cause something is called delay. Why delay? Because there is leakage. If I'm dedicating 5 voltage in this area, but then, because of this, it came 4.3, then the decision will be what? Delayed a little bit because I have to compensate it to be 5. That makes sense? That's basically what is written in front of you. So modern ICs, when I see ICs is integrated circuit or the chip, semiconductors, are fabricated at feature size smaller than 0.1 micron. There is even smaller than that. We have now 7 nanometer technology. They are working even to blow 7 nanometer technology. They're going into 5 nanometer technology. These type of chips, wire delays are significant as significant as compared with the clock period. So of course the clock is pushing inside wire, right? So that means you are delaying the clock. Then we will have a problem, and this problem will called what? Clock skew. Clock skew. Okay. So now we understood what's clock skew. Clock skews came from an equal amount of combinational circuits like buffer inverters between of the clock passes. Like, we already have here the device number 1 and device number 2. And here is you already have this connected to the like this. Here in the middle, look, did you see what I'm doing here? Here in the middle, there is a bunch of wires and connectivities, maybe combinational circuit, inverter, whatever. So that will cause that, this flip-flop will have a clock, and this will have this clock, but shifted a little bit. that case, these two guys are not synchronized. They are slightly synchronized. That's why we have skew. Okay, so skew refers to the absolute time difference in clock signal arrival between 2 points in the clock network. So when we say clock network, that means we have a bunch of propagate flip-flops and counters and registers, and we connected to them. Now it became a network, right? Because you already have a bunch of wires coming out. Caused by delays in the interconnect, within the clock distribution network, caused by the combinational logic used to selectively gate the clock of certain devices. Now, there are two different types of the skew or the clock skew based on the configuration. So what is this configuration? Maybe before I will jump to it, I need to go ahead and draw for you something. Here's the thing. So imagine that my circuit, it just have two flip-flops, right? So this one and this one. Here is a combinational circuit, and here is my clock. This circuit in front of us is what? It's a synchronized, right? This circuit is synchronized. This circuit, it's perfectly fine. This clock is arriving here and arriving at the same time because we are saying that this wire doesn't have any resistance, so there is no delays. That makes sense? Now we're gonna make some trick. What is this trick? Imagine the following. I added here a delay. So that means this one will push data, but this one will be a kind of lazy. If this is head and tails, then the head will be processing before the tails. And that this case of synchronization, they call it positive skew. Okay, that's called positive skew. While if the same circuit got the delay here. So this configuration is called what? Negative skew. And this is called what? Positive skew. Now we're gonna go into equations and all of these things. Okay. Here, positive skew mean that capturing flip-flops get the clock delayed with reference to the launching flip-flop as shown in the figure. Do you see? The clock delay came here. What is causing the clock delay? Somebody tell me. I said combinational circuit, right? It can be sequential with combinational circuit. So that's opened the door for me in exam to ask you to build a circuit here with a specific requirement, and then you will find the critical path out of it, and you will define the skew. That makes sense? Hello? Everybody aligned with me? It can be, because you're looking for the longest path, right? You're looking for the something is significantly affecting on the circuit. So that means you're looking for the longest one, right? That makes sense, right? Okay, so there is a bunch of equations. We can take it in a symbolic ways, but later on this graphical crooked thing that I added, you can just replace it with what? You can replace it with a circuits, which is basically what I'm gonna do. So if you look to it, we have two rules. We have to think about it in terms of mathematical form to describe this kind of what? Circuit crisis. Okay, so rule number one, that the time that I hit positive edge, I call it tick. So tick. Tick means that, I hit the positive edge, or tick, I can hit the negative edge, but I hit an event, right? So that's why I said it TCK, the time of the tick. The time of the tick. What is the time of the tick? It should be greater than or equal. When we say greater than and equal, what does it mean? It means that, the circuit will take it. There is no STA, there is no violation. Greater than or equal, there is no violation. Reverse, there is violation that we have to fix, right? So here, tick greater than or equal what? TP max. Do you remember this? Propagation delay maximum plus the TC max, which is the combinational circuit maximum, minus the T skew plus the what? The setup time of the second flip-flop. Okay? If you notice, this one will give you the maximum frequency. So this one will tell you what is your maximum frequency. Then rule number 2. This rule number 2 is trying to help me to figure out the whole time for the previous guy. So TB minimum plus TC minimum greater than or equal, there is equilibrium here, of the T skew plus the T hold time. Okay? Some observation, we're gonna get it, but you need to learn. What is those? Positive skew is good for the setup time. Why? Because it will increase the size of the setup time. But it will take from the time of the whole time. That makes sense? Do you remember? You have the positive edge like this, right? Here's the setup time in this area. Here is the whole time in this area. The skew in the second one will be increasing the TSU. TSU will be added like this. But the hold will be actually shrinked like this. That will cause a big problem for the TH, because the TH time can move like this. So again, put it as a conceptual thing. Positive edge, positive skew is a good for setup time, bad for hold time. Now, here is the derivation thing that of all of this equation. I put it up, but in a fancy way so you can follow. Think about it. Here is my first clock. The second clock came delayed. So the starting point of the second one delayed by the T skew, right? Then, we started with the TP max, TC max, and all the things. So we got the part here of the tech minus TSU, and here is the tech plus minus TSU plus the T skew. This is the margin that I will look for. And the second rule, this is the second rule. Look. This is the second rule. This is the first rule. This is the second rule. Okay? Now, let's go into the negative skew, and after that, I will start into what? Solving problems. So positive and negative skew is different, right? Negative skew, the master, or the head is basically the one will be delayed, while the tail will be arriving earlier than the head, right? So the one who should broadcast it to the second stage will be in trouble, right? Because this one already finished before this one starts. You understand what I'm saying? So it is the same equation of the tick of the positive edge of the skew, except the negativity in the positive edge will be flipped to be a positive in the negative skew. Then if you look to the second rule equation, you will find it's exactly the same, except skew will be here in negative. Look, there it was positive, here it was negative. Then you will come out into a conclusion, say, you know what? That negative skew will improve the whole time, but it will cause a problem for the setup time, because now, this guy will finish early. The question, you guys are following me? Is it so far clear? I'm looking for everybody to say yes or no, not just a couple of you guys. What was that? Ashley said something. One second. Can you go away? Can you go over BMN and BMAX again? Sure. That was, you mean that was from the last lecture, right? The BN and BMAX from the last lecture. That's propagate. That's come from combinational circuit. You remember when I said here is a combinational circuit, Ashley? So this combinational circuit, it has a propagate maximum and minimum, right? Do you remember that? You remember the one bitful adder when I made all of the gates and then, I put the delays and then I added and then I come into the conclusion, what is the fastest pass, what is the shortest pass. So this combinational circuit will have a rule into the tick and also the hold and setup time for the clock. So that's why TB max and TB minimum are there. I would recommend you to look into the first lecture of the timing. I think you're already there on the blackboard, and I think the number is called lecture 7. Anyway, we're gonna use the same resources we used before. You remember when I used such a kind of thing in the first lecture? And here is my circuit. So one of the questions I can ask you, this circuit in front of you, positive or negative? That's positive, right? Why? Because the delay happening in the tail, not in the head. Then we have a bunch of timing here. The clock of the flip-flop, any flip-flop, so that means those two flip-flop, no matter what. So you have here the minimum 7 and the maximum 9. And the combinational delay here is already calculated for you 4 to 6 nanoseconds. And the setup time for the flip-flop is 5 nanoseconds. Hold time is 2 nanoseconds. What we are looking for now, we are looking whether that we are in a violation or not. And also, we'd like to know what is the maximum frequency with the skew and without skew. Equation. What was the equation? This is positive edge. So that means I'm going to go to my equation here. So I will take the whole entire. So I'm looking for the bare minimum, right? Because, say greater than or equal. So I will take the bare minimum. So the bare minimum, TB max plus TC max minus T skew plus TCC. So TB max is what? Now it's coming from the clock flip-flop here, a combinational part of the flip-flop, 9 nanoseconds. TC max is coming from the combinational circuit, is 6 nanoseconds. Then the T skew here, it was 3 nanoseconds, I believe. So it's going to be 3 nanoseconds. Then my setup time is 5 nanoseconds, so that means 17 nanoseconds. 1 over 17 nanoseconds, that can give you what is my maximum frequency with Q. So have you noticed? The maximum frequency got improved, right? Which is actually proving that the setup time for the positive edge of the clock will be improved, while the hold time will be what? Will be getting bad, actually, getting worse. Of course, this equation we learned from the first lecture, you can remove the skew out of that. Then, you will calculate, again, it will be 1 over 20, which is the 15 megahertz. So with a skew in a positive edge form, we came into 5850.82 megahertz, while without the skew, we actually hold back a little bit and we shifted to 50 megahertz. That makes sense? Now we need to look into the whole time and the trick of the whole time and the violation. So here is so what is the big skew? So I'm looking for the big skew. So what is the big skew? This type of circuit with this requirement will be holding without any violation. Okay, what is the big skew that the above circuit can take while meeting the whole time constraint of this circuit and above? We already have the whole time here is 2 nanoseconds, right? So I can put it in this equation and I apply it to it, and I will find out that, my skew should be less than or equal 9 nanoseconds. In that case, my skew was 3 nanoseconds, so I'm safe, right? But if I found my skew like 11 or 12, then, there's violation. We have to either decrease maximum frequency or make modification on the circuit. I'm going to stop here and ask, is it clear so far? If it's not clear, tell me, I can slow it down more. Okay, now we're gonna move into the second possible thing, which is the second configuration, and see what would be the happening. So numbers will make us feel the statement we already have as a positive skew will be improving the setup time, while it will really hurt the whole time, while the negative skew will be actually hurting the setup time and improving the whole time. So here is the circuit. As I can see from the configuration, this is what a negative skew. So I'm gonna use the equation dedicated for this, and that case is not minus the skew, because minus will be positive. So that means my actually maximum frequency will be dropped, in that case to be 43, 47, and that show that setup time will be really effective. The second rule will give an indication whether that this setup time and the whole time and setup time will be meeting the 3 nanosecond in this case or not. So I'm gonna go into my equation, and I will find myself in a big trouble, because the skew has to be greater than or equal minus nanosecond. There is no time in negative, right? So you're gonna be a problem. So there is no possibility for this signal exchange can cause a whole time violation. Okay, but if you increase the skew 1, so instead of 3 to be 4, then you will be in a violation problem. Okay. Any questions so far? Question? Everything's clear? Now let me tell you some tricks about possible question can come in the exam. Do you guys like to hear this, or should I move forward?
Actually, can I hear that last sentence?
Yes, which one? Here?
Before, yeah.
Okay, so in that case, this possible thing that in front of you is telling you there is no possibility for this signal change can cause a whole time, because this minus 9 nanosecond, if you remember in the violation, I told you, if it's positive, you're fine, but with negative and you flip it, then it will be a problem. Because, you're gonna flip here, because, if you remember this comparative things, the negative is gonna go here, the positive will go there, then the skew has to be less. But if you increase the skew of this problem, instead of 3 to be 4, applied in this equation, you will find yourself in a violation.
So the way it is now, the skew can be as large as it wants.
Yes.
Okay.
Okay, that makes sense. Now, yeah. Questions might come in the exam. Type of question. Here is just a descriptive problem, right? But the skew can be a circuit, and you calculate the delays of the circuit. Then you will apply the rules, right? T combinational, it can be something else. It can be a circuit. To flip-flop like this, maybe the circuit will have both skew. Can have T skew positive and negative. Then you have to apply both and see what will happen, right? Instead of 2 stages like this, it can be 4 or 5 stages, right? And instead of the flip-flop, both of them have the same timing. They can have 2 different timing zone, like TSU of the flip-flop number 1 different than the TSU of the second one, and T hole different than the second one. That makes sense? And we know what is the critical path, what is the longest and the shortest, how can it be calculated. We know how to play with NAND gate and equivalency between gates. So that will make it easy for you to define the critical passes and long passes, short passes, all these things. Is it clear to everybody? Okay, so we finished the first part of the lecture, which is the timing. We have the second part, which is called glitches. And I'm gonna move this to the next next lecture. Okay, so I'm gonna give you the timing like piece by piece, so it will be easy instead of like camera use timing. Sounds good?
Awesome, thank you.
Super. Now we just play, okay? So what is the play we play here? Somebody's telling you, can you please build me the structure gate level of the BCD to accessory? How many of you are aware of how can you convert from BCD to accessory? Huh?
If we know the conversion through gates, the top of our minds, top of our
Yeah,
head.
it's basically 3. So you add 3 to 9.
Ah, okay.
So, you know, logic gates, think about it. Accessory is a table like this, right? What is the BCD? BCD is the 4-digit, right? Shad, you're right. So if you have BCD here, like B3, B2, B1, B0, and then X3 is X3, E2, E1, E0, 1, 2, 3, 4, 5, right? So you are, you know, this one is 0 to 9, right? There is no 10 and 11, that's a BCD, right? Then there you're gonna have it to be what, 3 to 12. And you will make K-map for every single E, and then you will actually implement it using the gate levels. And here's the gate level. One of the things I noticed, some of you have, maybe some of you are confused between the difference between of the using the assigned concurrent statement, and you consider it as a structural level. That's not a structural level. That's called data flow level model. Whatever in front of you now, it's gate level, structural level. Okay, have you noticed I'm using the gates here? So those are actually like a, you know, items primitive inside library, which have been optimized by the team of the Air Force who actually built the language. Okay, and IEEE, or of course, you know, adopted. That makes sense. So pretty much it's just implementing. You know, I'm implementing gates to gate, gate to gate, and so on. For instance, you know, I have like this circuit. I'm gonna give an example. So you already have here an and this and going like this to be like that, and X, Y, Z, right? And here is F. So in that case, if I want to do it with structure, I will make something that's called T, right? Then I would say and T, X, Y. What does it mean? X and Y will be ANDed, the output will be T. Then I AND what? Z and T, and the output will be F. So those are structural level of describing the circuit. Make sense? What I will ask you to do, I mean, can you please do that for me? Try to take this code, okay, and you implement it. And give me the next time, just come, everybody will write in the chat and say, I implemented this, here is number of resources. Okay?
Sounds good.
So again, let's make it even more fun. So what is the fun? You're gonna build this module by yourself. I mean, you take a copy of it, and you will connect it to LEDs, and you will connect it to switches and everything, right? You need 4 switches for the BCD, and you need 4 LED for the accessory out, right? And then you will calculate what lookup table, and you will calculate what flip-flop, and you will calculate for me the power. Using the same structure. And you will make a test bench to check the outputs while you're pushing data. Questions I would ask. What type of corner case I can have in such a kind of conversion module if I'm writing this bench?
Does it add 3?
Huh?
Does the BCD add 3 to create X's?
Yeah, but you know, you can think about something which is basically the corners, right? If I add 3 to 9, whether it's gonna give me 12 or not. If there is any 10 will happen. If I push 10, what the output will be? It shouldn't be anything, right? If I push 11, do you think 11 is exist in the BCD?
No.
Stuff like that. Those are corner cases, right? That makes sense? Of course, you know, I'm not asking you to do much, but you know, I'm just trying to help you to get used to the language. I have an idea. Why you don't make accessory counter. Is it doable? Is it doable? Huh? No. Let's think, we are now in a designing mood, If I like to make my own circuit, which will have a switch. So wait, look at this. Here's a block, right? This block will have 4 inputs, which is switches, right? And those will go into the 7-segment display. Now we are playing with 7-segment display, right? And LEDs. Okay? Then I will have a switch here. Sounds good? I will write here, let's say 4. Right? Then when this switch will be equal 1, the output will come here to be what? 7, because this is the accessory equivalent, right? And it will write to me here in a binary in the LED 7. Okay? Then if I put this 0, okay, what will happen? The output here will be 4, and representing here 4, that means it didn't do the accessory, just passed the output. From your point of view, how I'm going to build this circuit? Huh? Hello?
Using a box?
Yeah, this is a big box. Should I help? Or you think?
Can you repeat the question?
Again, I want to build a circuit using this model, right? What it does is the following. I have a box here, and this, I have a box in front of you. The input of it is 4-bit switches, right? 3-4 switches, right? And the output will be, you're representing the output in the 7-segment display and an LED. The 1 digit that we are learning so far, right? That makes sense? Now, if I push these switches on the right 4, that's an example, right? The output, it should be either coming with the accessory value, or it will be just presenting the whatever, I push and switch it at the PC. Based on the switch here I have. So how I'm going to build such a kind of thing? Should I do it?
Could you make it so the select input is tied to a mux, which either selects the 4 input or the incremented 4 plus 3 input?
Yeah, you're right. I mean, you're doing good. So, here, I'm going to show you what I'm going to do, actually. No, look. Basically, I have here this block, which is the accessory. So I have here the switches. And those connected to the board, right? Then I will go like this. Sound good? And here's the output. Then I will come here like this. That's another switch, right? 0, 1. And those will be connected to the LED, and those will be connected to the digit. You remember the digit I made in the 7 segments? Those 4 will be connected there. So look, if I push here 0, then the output will come as a what? Accessory. If I push here 1, the output will come as a what? Just a BCD. That makes sense?
Yes.
Is it clear to everybody? Huh? No.
Yeah.
Now, I'm gonna tell you the story of the memory. So before we start, I mean, the first lecture I started, I was telling you about there is data formats, and there's something that's called wire, and there's something that's called reg, and we started all of these things, right? Everybody agree? Now we came into a conclusion. If I would say reg, and then I will go like this and say that most significant bit -1 to 0, and then I will call it, for instance, X, right? And then that will give me like a bus, and this bus will be how many bits? Let's say most significant is basically 3, so it's gonna be 4-bit representation of X. Do you guys agree? That was how we actually building register, right? But now we have 2D register. We have what? 2D register. What is 2D register? It means the following. I can just come and say, great. 70, and I call it mem, and I say here 15. What does it mean? It means that I have 16 locations. Each location is 8-bit. That's a way of representing 2D register. In terms of data, that's the data. Still, we have to format it inside stuff and so on. That makes sense? Before, I left it here empty. And the empty by default, that means it's just 1 row. There, you already have how many rows? Sounds good? So I think it's a time for us to go and flip into Vivado. So Vivado. Well, I'm waiting for Vivado. I will do something in front of you. If I build a memory, how would its memory would look like? Normally, my memory, it should be like this. That's called memory. It might have a clock. It might also have a reset, right? And it will has data in bus within it, and it will has data out in it, right? Then I need to push data inside the memory, and I need to pull data out of the memory. Do you agree? So the memory is like this array, and each of those are in bit. So I need what? Also, I need a pointer, which I call it address bus. I can call it address bus. In that case, I have to be reading or writing. Are you guys following me? No. So one of the way I can design my memory to be like this. If the read is equal, read and write is equal 1, that means this address bus is helping this input to go inside the memory. While if this will turn to be 0, so the address bus will be pointing to which data will go out. So that's called what? Single address plus memory. So this memory can read or write. It cannot read and write at the same time. That makes sense? Hello?
Yes.
Now, this memory has a pros and cons, right? You have to wait. So that means you might get into something that's called idle situation. That means you have to stop waiting. Let's say there is another block here, right? And this block is waiting for something. So it will be like still writing to the memory. I'm gonna have to pick up data out of this memory soon, right? So I have to read data out of the memory. Now there is a different memory, which is basically more fancy and more hardware resources will be used for sure. Here is my memory, and here is the address. All right, and here is address read, and here is clock, here is reset, and then here is what data in, and here is data out, and you can have here read, write, enable, or you can if you don't want. So in that case, somebody will tell me. So basically, this one would be responsible for moving the data, writing data into the memory, while this one is picking which location would be reading out. So that means I read and write at the same time. That's called what? Multi address pointing. But still, it's called single memory. You know why? Because there is single input, single output. There is another memory, which is called like this. Data N1, data N2, clock, reset, then address, read, and address, right? And then, selector. What does it mean? It means I have two input ports, one output ports of reading data, while this address will be selecting based on this select whether this data will be written here or this data will be written there. But this one will be responsible on just picking it out. Of course, you can imagine anything you want, but then what you are doing, you are adding more what? You are adding more resources. That makes sense? So I'm gonna build one in front of you and let's see what will end up. So I don't know where is my Vivado. Here's my Vivado. So now let's go and say yes. Everybody can see my Vivado? Hello?
Yes.
Okay. Okay. Just one second. I don't know why my Vivado is not there. Okay, so I will say here next, we call it what? Memory, right? Memory. And then, RTL XE7A XE finish. Add create a constraints nexus. ODR. You guys still see my provider, right?
Yeah.
Okay, just let me get my XDC somewhere. It's here. Now we're gonna say create design, and I will call it what mem. I would love to write it on hand. You know, since we started, I told you about the parameter things, right? So I would recommend to do everything parameterized. So what type of parameters this memory can have from your point of view? I can tell you one of the parameters we might have is how many bits the input and output should be, right? Do you agree?
Yeah, that could be one.
There is another one, the depth of the memory. How many locations in the memory we have?
Mm-hmm.
That makes sense? Which is coming out of what? The resolution of the address, right? Let's say my address is 5-bit. That means this address is pointing to how many locations? Huh? 52 locations. So I need here, and this parameter, we'll call it what? Data with, and it's equal 52. Data. Now we're gonna go into what we need. Clock. So gonna be input clock. Input. We need write enable. We need a read enable. We need address write, which is gonna be input something. Okay. And then we need input address read. Then we need input data and when we need output register, of course, and it's gonna be data out. So far so good. But then we need to check what those sizes are. So basically we're gonna do the sizes. So address write is gonna be the not this. It's gonna be a address with -1 to 0. Then we need then also the outputs here is gonna be the same size. You guys know what I'm doing or not? Is it clear to everybody what I'm doing?
You're parameterizing the basic aspects of the memory.
error. Yeah. So now the addresses, it has to be address widths, and then the data, it has to be data widths. Okay. So we build up this one. Now we need what? We need to make internal variable. And this variable is going to be the new one we already made, right? But before the internal variable, I will actually make something more fun, which is basically, I'm going to make a new parameters. And this parameters, I can make it like this and say parameters. Parameter is parameter RAM depth is equal 1. What does this mean? Somebody tell me. We learned this sign in the first or the second lecture.
You're shifting it?
Yeah, that means I'm actually making mask. It's like I have 8-bit, I'm shifting it. That means the whole dipset will be what, 256. I'm putting one in every single location. That's shifting, right? Pushing. That makes sense? We can take this out if we want, because those are global for me. I can put it here. What is the problem? So what? Leave it for now. Okay, anyway, now we need to start processing our memory. So in that case, we have to go in what? Define internal variable. I'll fix this later. Anyway, so I would say reg data width -1 to 0, memory 0 to RAM depth -1. So what I did now, I built the memory skeleton, which is basically a register 2-dimension. That register, every single location will be data width -1 to 0. And I started from 0 to RAM depth. Do you remember when I told you can make most significant, least significant, or the reverse? So I just start making from the 0 to the depths. It's up to me, I'm just trying to check. Now I need to build what? I need to build a 2 process. So how can I push data inside? So the read and write process, how it's gonna be? It's gonna be based on what? The clock. So I'm gonna make here memory write block. Writing operation. Writing operation. Then I say here always over the edge of the block. I don't need a reset, by the way. You know why? Because if I make a reset, that means I'm gonna make it a hill of resistors. They're gonna be a big combinational circuit, which is gonna be really costly. So here I would say in the beginning, I can make it a name to be more clear. I'm writing, so I would say F write happen. Then mem address write will be equivalent to data. That's it. Okay. Then I will go here. memory read block reading operation. And always at positive edge of the block. And then if need happening, data out is equivalent to mem address. Is it clear to everybody? What I did now. So we have two processes, right? The memory is like two halves like this. One half is taking data from the data port input, and one is actually pushing the data into the output. So this one is taking the data from the input. This one is taking the data and pushing it in the output. Is it clear to everybody? I make it look up. Is it clear, everybody? Hello?
Yes.
It can be local program or cannot be, it doesn't matter, you know? It's up to you. So if you run a test bench, how are you gonna test it? So somebody tell me. What type of operation in the test bench it need to be done? Excuse me. Tell me. What type of test bench you should have here? What is testing? It should be testing the boundaries of the memory, right? Like, you know, what is the depth, how far you can send data and all of these things, right? So we can try something, which is writing the test bench, because I'm gonna teach you a trick now in the test bench. So create simulation. And we call it what? Mem TB. Then they're gonna be what? They're gonna be mem and then you know they something from there we can make a fancy test bench parameters. So we'll put it, and we'll put it data TB. Well, 8. Address TB. I'll just call it 4. Then cool. You gotta follow me, right? Then I don't need those anymore. Why it's mad from this one?
You need semicolons?
Oh yeah, that's true. Not where, I forgot my reading glasses. We done. Right, so gonna be clock. Right. Read. Add this right. Add this. Read. Okay. What we can do now, we need to see whether that everybody understood the idea of the forever. How many of you remember forever?
I recall it being used. It's one way to make the clock.
Yeah. No, you use it in the test bench. You have to use it. It's only usable. Yes, you cannot use it in hard You're right. You're right with that. Go ahead. I have also a very good idea. I love ideas. Where was the sign I made it before? Edit. Define time step. Then what do you think? More fun, right? You see what I did? So I used define to give me what? To give me the time step instead of writing by my hand the time step. You know what I mean? Okay, look. Now I need initial. And I will say right in the beginning of 0, 0, and I wait here for like 10 times. Then I say maybe right is equal 1. And then I can make I can make 4 I equals 0 I less than Why it doesn't like it? 1 second. Let me fix it. Maybe I can put it here.
Professor, is it possible to see how you defined the time step once again?
Huh?
Is it
Yeah, here.
is that a is that a semi or just like a comma at the beginning of define?
Oh, it's a shift and then a space and then do you remember the thing in the top of the tape, the tab?
The tab.
Yeah. So
Oh,
above the tab there is like a little bit tiny thing.
I see.
It's a tricky, you know. So you have to push shift and then the space and then you will go there. Then it automatically will generate it for you. So fixed. Now it doesn't have any problem with the for loop and it loves the for loop. And we cannot be met from the for loop, right? So in that case, we come and say data in. You know what? We need also to be nice to data in equivalent to 0. What we can do, you know what? We can come and make something like this. And this, right? Equal this, right? That's one. Then we have to go here and to be also nice to the address. Right. You guys are following what I'm doing? Sounds good? What we can do, we can be even fancy here. Okay, let's run simulation and see what will happen. That's perfect. Did you see what happened? Look. The counter increment itself, right? Up to F, right? And then it stopped because I didn't ask for anything else after that, right? But then what happened? Data out is still what? 0 because I didn't read anything. But I need to see mem. So I can stop here and I say, can you please come and show me mem? Mem, it has all of this excess. Why?
Should the clock it should be pulsating, no?
The clock is not pulsing at all. Why?
I think you forgot the tilde.
Is it? Where?
Where clock equals just clock.
Oh, you're right. Oh, you're right. See, even myself, I'm doing mistakes, right? So that's showing you that you have to be very careful. And I'm writing. I don't have even a piece of paper in front of me. I'm just writing from my head. So, and that should be use case too, right? Look, now it's actually going, and you're right. So, and you notice also the address counter was running without what? Without the clock, because that's a testbench. Now the whole thing, see, it actually makes 0 and then X and then 0 and then X and 0 and then X and then 0 and then X and then 0 and then X and 0 and then X. Do you know why? Somebody tell me why. Look at my code and you will figure it out. Why this happened? if you look at it very careful, you will find that X came in the middle of what? You can actually drag this like this and say, you know, start from scratch. Look, this happened because of this thing I made here. So what I'm saying, increment and then wait 10 nanosecond or 5 nanosecond. 5 nanosecond is nothing. So it has to be 2 times 2. That should be 20. Right? So if we run like this, now the memory came what? Look, zeros. So you understood what happened, right? Hello? So basically, you know, that step time is not the clock. Step time is not the clock, it's half of the clock. So what I can do, which is better than this, I can just say 10, right? And then I go into the clock itself and I said it's like this. Then that can be 10 as before, and that's gonna be 1 as before. Or, you know, I just make it 1 generically, so you can just change it, you know? So, you know, you can remove the 1, but I like 1 because maybe I can change numbers, right? You can also make a lot of list of parameters there and change this one so you can make more generic. Look now, so if you go here, memory, grab it here, and you can say run. Look, now it's here. And I can say stop here because, you know, we are running a lot. I didn't say finish for the test bench. So everybody understand what I'm doing now, right? So what I did, somebody tell me, give me a summary. Who likes it? Talk to me. Mario, what did I do?
There was a timing issue and you fixed it so we could see.
Yes,
No?
and instantiated, and I filled it with 0, exactly. And also, you know, I timing issue, like Mario said.
Oh, wait, you instantiated the output? Or no?
Yeah, I mean, I instantiated the memory. That's what he said.
Oh, okay.
Right? And then, you know, I left it, by the way, the right high. Have you noticed? The right is high all the time, so keep writing. See, the right is high. If I want it to be not high, I can just come and say right equal 0. Then I make like this. What happened? The right went down. If you don't include the time step, would the code not work? It can just go like stand like this, you know, it will not do anything. It will be like a garbage, it will do nothing. That makes sense, guys? So now I need to add an aspect which say that, you know, it changed the writing, right? So maybe I can make an Let me think. What about if I make something really, really, really cool, which is, look at here. I can here come and say reg mem test, which is the size of it, data TB -1 to 0. And location wise, it's going to be 0 to -1. Okay, then look, I make it equal. So I'm trying now to fill it with constant values. I want you to think with me about this. Look what will happen now. And then I will put here what, how many locations we have in this memory. It's the 4 locations. Do you guys agree? Is it 4 locations? Oh, that's also another thing we need to think about. What is this memory? How many locations? It has a 16th location. Why 16 location? Yeah, it has 16 locations, right? So we need 16 locations. Look what I'm gonna do now. Okay. What is this error? Oh. You know what I'm trying to do, right? I'm trying to fill an array and I call it. You know what I mean? It should be fine. It should be, maybe I have to make it like a, what is the size? Is 8H45. 8H20. 8H12. H. I think something is not correct. One second. Anyway, I will find it for you, but there is a way that you can fill an array. You understand what I'm doing, right? And I will call the array to be filling the memory. You understand what I'm trying to do? Hello? Yes, I'm giving a default value. So what I can do something else. I can come and say data n is equivalent to data n plus 1 or plus yeah, plus 1. Just say plus 1. Let's see what will happen. So I'm gonna make incremental inside the memory. So I believe first location will be 1. So here the memory, here the memory. It should be 0 and then 1. So let's clean it up. Look, so now it's 0, 1, 2, 3, 4, 5 up to F. You see what I did? So I just make a dynamic counters inside here with the add memory. That part is sequential. Have you noticed? Because I can click it like this and see what will happen here. Let's see now. Run simulation. Still fine because it's parallel, but there is a way to make it sequential. So you have to add time in it. Look, 0, 1 to 3F. But what about if you add time here? Yep, here the time did it exactly as I want. So it's actually jumped, it skipped 0 and it moved to 1. See, 1, 2, 3, whatever. You guys are following me? Hello?
Yeah.
Hello? So you understand what I'm doing, right? I'm trying to, I don't want to fill the first location with 0. So what I did, I tricked the counter. So what I said here, I said, go count 1, so I don't want 0, right? But in that case, increment the address. But then, the address came after 1. So that means, the data n is 1 and the address will point 1 there. You understand? So I took more time, if you notice, to do this. So now it's 1 to 3 to 15 to 16, right? I can, still data out, I didn't read it. Data out is still 0 or whatever X because, we didn't have anything there. So from there, I can come here and say, after 1, whatever I say, RD is equal 1. So pretty much I know that my data, my address read is 0. So automatically, what is the value will be there? It will be whatever written in 0. So it should be 1. So let's see. And then, what we can say, for instance here, wait for some time, which is this time. And say, wait for instance, for 100 cycles. And from there, you can just say, finish. After 100 cycle, finish. So I'm expecting that by the end, the value of data out will be jumping to whatever was written before, and we wrote 1, so it should be 1, I believe. So let's see. What happened in front of you? Hello? Did you see what happened now? That point to this point, it was the amount of time I asked it for to give me the output to be officially here 1. From that time. See, and now read is when high forever. You know, you can pick anything you want. You can just come and say, for instance, after this, I don't want to read this. What I can read, I want to read another location. So I would say address, right, read is equal 3. So I would like to read value of number 3. And then, you know, I can just say, give me more 100 or something. And then, you know, I'm expecting 100 after 100, right? I'm expecting 1, and then, you know, 100, and then, you know, another value, which will be location 3. So it should be 4. So let's see. See, so address read here, it became what? Number 3. In that case, you know, when number 3 came, data out, but data out didn't change. Have you noticed that? Are you following me, guys? Have you noticed data out didn't change? Is there any idea why data out didn't change? Even actually location 3, it has 4. Any explanation? Hello? That's basically what I'm gonna do, because, you know, I went inside now into simulation behavior causing this. So I want to see whether that you guys will figure it out or not. That's not a part of the thing. It's a part of the simulation has problems. We need to think about it. The hash should 4. So why did the out didn't give me? Why did out is fixed? Even, you know, RNG changed here, and address read is. Oh, address read is still 0. Why address read is still 0? Address read is still 0. Interesting. Why address read is still 0? Even we change it, right? So that's the problem. So that address read didn't change. See, I'm showing you now debugging. So we are debugging together. After that, we're gonna summarize the whole entire task. I think it's a stability. Address. That doesn't make sense. Any suggestion why the address read is still 0? That's a corner case, by the way. So is there any suggestion, guys? Hello?
I suppose since it can't reach, if it always 0, that means that something in the code isn't reaching that statement. It could be something to do with the for.
By the way, address read now it's changing, but still the data out. That means there is something wrong in the design. We have to go and check it. What is the problem in the design? See, that is the problem. Huh? Corner case, R&D. Did you guys figure it out? Typo, exactly. And that is 90% of your problems too, right? Which is good, you know. Let's see what will happen. Is it reading or not? Okay, so now, did we learn anything out of today? I know. So now, did we learn anything out of today? Testbench is the very important thing, right? The most important thing that we learned today, testbench is very important, because other than that, you will spend a hell of time of figuring out what is the problem on the board itself. Do you guys agree? Let testbench figure it out. Let testbench say that, you know, this thing is not changing. So what does it mean? So summarizing what we have today, we learned about, you know, there's some existence of communication protocols. We talked about all of them. We said we need one of them, which is very critical. All of them actually need one of the most important things, which is called buffering. And then we talked about the timing. We specifically, we talked about the skew, synchronizations, the two rules we have to follow, whether the positive skew versus negative skew. Positive skew, we said the timing setup time will be improved while the hold time will be degraded, and you know the vice versa will be for the negative skew. We said the positive the setup time will be affected in a negative way while the hold time will be improved. Then we talked about the accessory. We covered the accessory for the BCD with a trick asking you to display both the BCD and accessory by switching using multiplexer track. And then, you know, we start talking about how can you use the 2D dimensions register data type on the Verilog for building a memory with a different type of configuration. And we picked one of them, which has 2 pointers, one for reading and one for writing, with enabling the situation while you're reading and writing. And of course, this type of memory can read and write at the same time. And we wrote the code in front of you. We made a mistake, some of them intention, some of them non-intention. And then, you know, we developed a test bench. We added the test bench, multiple things that we already learned before, which is a forever. We learned also how to use the define for defining the time step for the clock. And then, you know, we start having a full loop inside the initial block for iterating things faster. Definitely, you know, watch it. It's very good. But, you know, I really enjoy actually teaching you guys. You are really guys are really good. And by the way, I mean, I'm expert in hardware. I mean, I've been working for hardware for years and years. So basically, I wrote stuff like that, while I'm sitting with you. So I don't have material in front of me. So, we are working together and we are learning from each other. So that's really good. Do you guys have any questions? Hello? Rest of the folks. If you have any questions, don't hesitate to ask. If there's something not clear, also don't hesitate to ask. I just really like you guys to learn and enjoy what you are doing. And I will do my best to help you as much as I can. And thanks so much for attending the course and attending the lecture today. And keep in touch. And God bless you. Stay safe. Thank you. So we are done for today. I appreciate it. Thank you.
Thank you, Professor.
Thank you. God bless you. Stay safe, okay?
Professor,
Yes, sir.
can we talk about USBs for like a bit on?
And you mean in the course? Of course.
Oh no. Like
No?
my question is like at the moment, like USBs can take out any serial communication they're given,
Yes.
essentially.
Yes. That can. I mean, USB is something very huge. Okay, it's a multi-protocol. It's not just one protocol.
I see.
But it has a serial communication. It has a topology. It's like network topology. So in networking, you need to know that the network is a 7 layers, and those the same thing. It's a 7 layers. So you have to learn all of the layers. How can you move from one to the others? How can you get feedback from one to the others, and so on.
I see. So that's probably its architecture would have to be
And
looked
this
up.
architecture is more into 4300, basically, the one I'm teaching.
Oh, I see. So if I wanted to use like UART with like a module that I purchase online, could I program a PMOD to interpret that UART?
Definitely, I can do this. This is one of the things I'm gonna do in front of you guys in the lecture, maybe in a week or 2 weeks next.
Now, let's say I have two modules and then one uses UART, but the other one uses I²C.
It doesn't matter because there is a designated area in XDC for each PMOD, so there is no interference between of them.
But what if I wanted the two modules to communicate with each other? Would I have to?
That should, if it's gonna be in the same board, you don't need to do it through the XDC. You're gonna make it blocks talking to blocks, right?
Mhm.
If you are across other board, then you have to make them talk to each other.
Is there a way to convert these serial communications into other serial communications?
Yeah, of course, but there is a lot of constraints. So you have to build a customized finite state machine to move from one to the others. And also you have to think about the benefit out of that.
Out of having the two talk to each other.
Yes, I mean, of course, there is also there is a penalty for this, right?
Mhm.
You're gonna do something from the performance. You're gonna do some other stuff. That's why people did you see those guys in Amazon? They sell HDMI to DVI converters, whatever to convert that to convert. This stuff is finite state machine written in a chip.
Oh, okay. No, yeah. Because I see.
So of course, if you use an FPGA for that would be a hell of money. You can make a lot of money. Of course, with the 3D printers and stuff like that, wow.
So there isn't any conversion within
FPGA, I don't think so. I will tell you something which is even more fun. I have one of my cameras here I play with, but my desk is the most organized desk in the nation. So I will find it. Yeah, here. This camera, imagine, it has an FPGA here in the back.
An FPGA entirely on the back.
Yeah, it's Altera. It's Altera Intel. This chip. So you can actually play with to program it. It will do multiple signal and image processing and video processing analysis. So you can do the same thing. You know, actually, one of the things I really like to see. Do you remember the Mac, the Thunderbolt communication protocol?
The Mac Thunder.
Yeah,
Thunder-
the Thunderbolt. This one, you know, this is called Thunderbolt, whatever Thunderbolt communication.
Oh yeah, yeah, yeah.
There is no one for USB, VGA, and stuff like that. There is nothing like that. If you study it very well and you understand how it works and you make a reasonable design for it, people will buy it. A lot of people are asking for it.
Oh, so that's Apple's own version of communication, that lightning bolt.
Exactly. Everybody has his own communication. So there is actually other communication protocols you never heard about, which is like AMBA bus, AXI bus, Avalon bus, BBPA bus, stuff like that.
I see. So if no, I think for the most part I understand it. As long as just in a way you can gather any information you want from a module into your FPGA, and then you can program it however you please with that information using an SDK, and then you can have just about anything.
Like these two guys. I want these two guys to have a communication together, right? Think about it. What I want to do. I will maybe make a P mod here, P mod there, and then you out, and they will talk. With a wire, right?
Yeah.
I make a wireless here and wireless there, and then making them to talk to each other. Then it has a commutation than different this one. And then they will be working in a cluster. The computer will be looking for both of them to finish the job.
Now, well, if you could possibly connect an FPGA to like a microcontroller, no? Just to...
Yeah, I mean, one of my students did a very nice thing. He built a radar system. He actually put it on the FPGA, but then he used the analog part of the microcontroller out from the PMON, and he built on the Visual Studio on the screen a screen for the radar with like a greenish thing, and the colors, and the dots greenish of the
to interpret all the radar data.
Oh my gosh! And then we have this ultrasound sensors around, and with the motor, like step motor going around, and it's just going like this.
I see.
And we put it in the top of RC car, and now we are trying to put it in the top of the drone. So it's gonna be like a wax system. So all of this can be done by learning this itty-bitty tiny stuff when you put them together.
No, yeah, for sure. Well, thank you, Professor. I just want to
have a wonderful day. Okay, stay safe. God bless you.
Yeah, for sure. Sorry.
Thanks, man. Do you have a question?
No, I don't have a question. I was just listening.
Oh, okay. Okay.
All right.
God bless you. Okay?
Bye-bye. Good day.
Bye-bye.